We are going to take a look now at factorial analysis of variance, or factorial ANOVA. So in one-way ANOVA, in Chapter 21, only one variable defined our groups. So for instance, our example involved ethnicity of families in the special needs adoption study. Families were categorized as minority interracial, white interracial, or transracial. So there was just one variable, that being family ethnicity. Now, in ANOVA, a variable that defines groups is called a factor. In two-way ANOVA, two factors define groups. And a factorial ANOVA is an ANOVA with two or more factors. For our example, let's use two variables from the special needs adoption study. One will be handicap status, and the other will be whether the adoptive parents were prior foster parents to the child. So handicap status and prior foster parent status, these are our two factors, and our dependent variable will be the score on the parent-child relationship scale. And in ANOVA, you know that the dependent variable is a numeric one. In ANOVA, a level is a category, or we could say a value of an ANOVA factor. So for instance, the factor handicap status has two levels, and those would be child has the handicap or child does not have the handicap. Our ANOVA example has two factors, each with two levels. So there we have here two factors. The first number conveys the first factor, the second the second. The first number is a 2. That conveys that the first factor has two levels. The second number is also a 2. So that's conveying that our second factor also has two levels. So we have got a 2x2 ANOVA. And our ANOVA, in essence, has four different groups. Children with handicaps whose adoptive parents were prior foster parents. Children with handicaps whose adoptive parents were not prior foster parents. Children without handicaps whose adoptive parents were prior foster parents. And finally, children without handicaps whose adoptive parents were not prior foster parents. The table at the top is presenting descriptive data for our four groups and for the full sample. So for instance, among children with handicaps whose adoptive parents were prior foster parents to them, the mean score on the parent-child relationship scale is 3.59. The standard deviation of those scores is 0.52, and there are 81 children in this group. Now, a factor's main effect is in essence the effect disregarding the presence of the other factor. It's the accumulated effect. So the main effect for a child has handicap versus child does not have handicap is given by the 3.38 versus 3.33 difference. And the main effects of prior foster parent versus not prior foster parent are conveyed by the difference between 3.46 and 3.26. So you can see that our main effects are showing that prior foster parents are tending to have, taken as a whole, higher parent-child relationship scores than do those who were not prior foster parents. On the other hand, the main effect for handicap versus not having a handicap, this is a much smaller effect. The difference between 3.38 and 3.33 is much smaller than is the difference between 3.46 and 3.26. Now, an advantage of two-way ANOVA over one-way ANOVA is that two-way ANOVA can assess two main effects. It's sometimes, perhaps often the case, that the power of each of these tests is greater because of the inclusion of the second factor. Now, these advantages are reasonably modest advantages. The increase in power, for instance, is likely to be quite modest, and further, it's just about as easy to conduct two one-way ANOVAs as it is to conduct one two-way ANOVA. Now, the really big advantage of two-way ANOVA is that two-way ANOVA can assess whether factors interact in predicting the dependent variable. We first encountered interaction or interaction effect in Chapter 11. So the idea behind interaction is the association of each factor to the dependent variable differs according to the level of the other factor. Here is the ANOVA table for our two-way ANOVA. And I note here that the main effect of foster parent status is indeed statistically significant. On the other hand, when we examine the effect of handicap status, which is to say, do we have a statistically significant difference between those with and without handicaps in terms of parent-child relationship score, that difference is not statistically significant. An asterisk or star sign is often used to convey an interaction term. So we have an interaction term that's tested, the foster parent status times handicap status interaction. And that effect is indeed a statistically significant one. So in essence, this is conveying that the effect of handicap and also the effect of foster, that these effects are contingent on the value of the other variable. So we'll talk a little bit now about how we interpret this interaction effect. Again, interaction is the notion of different relationship in different groups or different relationship in different situations. So one way that we can interpret our interaction is this, that is that the size of association of prior foster parent status to parent-child relationship differs by handicap status. So for instance, for children with handicaps, outcomes are much more positive for prior adoptive parents than for others. So the difference in these subgroups was 3.59 versus 3.13 on the 4-point outcome scale. A fairly pronounced difference. We won't bother to interpret it in terms of standardized mean difference, but you can see that it's a larger difference than is the case for the group of children without handicaps. In this situation, outcomes are only modestly more positive for prior foster parents. There's the difference, 3.41 versus 3.28, a smaller difference than above. And there's also a second way to look at the interaction effect here. The second way we could look at the interaction effect would be to look at the fact that the direction of association of handicap status to parent-child relationship differs according to prior foster parent status. For children whose adoptive parents were prior foster parents, outcomes are more positive for children with handicaps, 3.59 versus 3.41. On the other hand, for children whose adoptive parents were not prior foster parents, outcomes are more positive for children without handicaps, 3.28 versus 3.13. So in real-world research, one just chooses the best interpretation that they can. I guess I like the second interpretation here, which is to say that the direction of association of handicap status to parent-child relationship score differs according to foster parent status. Most statistical software package ANOVA programs will plot mean scores for your different subgroups. So here you're seeing the mean scores for the different groups on a plot. And I'll interpret the interaction in one way. You can see that where you do not have foster parent adoption, the outcomes are more positive for the kids without handicaps. But where you do have foster parent adoption, the outcomes are more positive for the kids with handicaps. Basically in ANOVA, where you see lines crossing in the plot, that conveys interaction. And more generally, as I'm stating here, it's markedly different slopes of the two lines that convey the interaction here. And sometimes you're going to have more than two lines on your plot, and that will happen if there are more than two levels for one of your factors. Now, the tricky thing about ANOVA, I think, is that when you've got an interaction, the interpretation of your main effects becomes problematic. In essence, there isn't a single main effect, but whatever effect there is differs according to the level of the other factor. So there is no straightforward interpretation of main effects when you've got interaction. The best thing that you can do in interpreting your results is to do a good job of describing the interactions. Now, in this particular ANOVA, the interaction term was significant. Now, if an interaction term is not significant in an ANOVA, what is usually done is that the term is dropped from the ANOVA. In other words, you run the ANOVA only with main effects. Now, let me point out a somewhat technical point, but even so, an important one. This ANOVA was run using SPSS. And note that the sum of squares used is the type 3 sum of squares. This text has only given you very general definition of sum of squares, but the sum of squares can be calculated in some different ways. And I recommend that you calculate the sum of squares in a two-way ANOVA, or in any factorial ANOVA, using what is called the regression sum of squares or the unique sum of squares. SPSS uses the term type 3 sum of squares to refer to what are often called the unique and regression sum of squares, but these produce results that are much less likely to be misinterpreted than do the other sums of squares that are often used. The text has some notes on different types of sums of squares. So we covered factorial ANOVA. There are some other extensions of ANOVA as well. Something called the analysis of covariance adds interval ratio level predictors to an ANOVA. So in our ANOVA we had, for instance, two factors. One was handicap status, the other was foster parent status. Each of these is a categorical variable. Each of these is a dichotomous variable. And basically, as we use them in the ANOVA, each of these was defining groups. So you can also add numeric predictors into an ANOVA. So for instance, you could perhaps add children's age, or perhaps the number of years that the child has been in the adoptive home. In all of the procedures that we've run in this text, we've had only one dependent variable. There is something called multiple analysis of variance that has the capability of assessing several dependent variables in a single analysis. I will mention also repeated measures designs. These are in essence ANOVA-like designs in which a single dependent variable is administered at multiple times. You'll need to check some other resources, obviously, to learn more about these procedures. Now, I'm only going to give you an overview of some other advanced multivariate statistical procedures. Well, in chapters 10 and 11, we studied causal models. So what structural equation modeling involves are really two things. One, we build oftentimes fairly complex causal models showing the effects of particular variables on other variables. And indeed, you know, one variable might be a dependent variable with respect to a second variable, and then on the other hand it could be an independent variable with respect to another variable in our model. So we have causal models similar to, but more complex than we covered in chapters 10 and 11, but also at a couple of points in time I've talked about the fact that sometimes there is measurement error involved in measuring a concept. So for instance, suppose we're measuring a child's behavior. On the one hand, we could have the child fill out the measurement scale, presuming the child was old enough. The child's parent could do so, and perhaps a teacher at the school. Then we would have three different measures of the child's behavior. And so this is the other defining characteristic of structural equation model, the ability to build in multiple measures of concepts. And this can serve to reduce bias and make the models much richer. So structural equation models are really pretty nifty kinds of things. Now then, what's multi-level modeling? I'll note that sometimes really complex structural equation models do multi-level modeling, but what hallmark of multi-level modeling is examining the contributions of variables at multiple levels. So as an example, suppose that we're looking at the reading performance of a second grader. Well, we might look at things like family situation, in other words, the resources in the family, the socioeconomic status of the family. We might even have variables about the number of books or resources in the child's home. We might have a variable that had to do with the amount of time that the parent spent interacting with the child. So all of those would be examples of predictors of reading level, or possible predictors, and all of those are gathered at the level of the individual. But we might also gather information at the level of the classroom, so that, for instance, we might look at the reading levels of other kids in the classroom. So that the idea would be that if the child is in a classroom where most of his classmates have high reading levels, well, does that affect the reading level of the child? So this variable is not at the level of the individual, but is rather at the level of the classroom. And then finally, it might be that we could even look at a school or even school district variables. Now suppose we have data from multiple school districts, and we could look at variables such as the amount of funding per pupil, or the median income, perhaps even, of families in a school district. So then that would be an example of variables at the level of the district. So this is what defines multi-level modeling. It's bringing variables at different levels into the prediction of the dependent variable. Now, survival analysis, originated in medicine, and it's the preferred method for analyzing when the dependent variable is time to occurrence. So let's suppose that you've completed an intervention for kids with issues pertaining to juvenile delinquency. So then we're going to have a follow-up time for, let's say there's 20 kids that you've worked with, and what we're going to do is we're going to go to the police records and we're going to look to see the timing of the first arrest. So, for instance, if you finish your intervention in, let's say, January, and then in September you see that Johnny has had a arrest. Well, that's about 8 months if we're going to code to the month. Johnny's dependent variable would be an 8. Now then, if Sally was rearrested next January, well then she's been 12 months prior to her arrest. Now what about Fred? Now we follow up for 3 years and Fred has no arrest at all. So in a straightforward analysis, I mean, this would be tricky. How should we code Fred? Should we drop Fred from the analysis? Should we give Fred a 36 because Fred survived for 3 full years without arrest? Well, I mean, it's tricky. But, I mean, what survival analysis can do is handle dependent variables that involve time to occurrence. It can handle those really well and without throwing out information. It knows just how to build Fred into the analysis along with the prior 2 clients who you worked with. Okay, a final multivariate procedure that I'll mention is factor analysis. So what factor analysis does, it reduces information from a larger group of variables into a smaller number. So let me try to give you an example. Well, suppose that you have 7 items on a child behavioral instrument, and these are hits others, isolated, fights, keeps to self, talks back, timid, and swears. Well, if you look at these problems, your mind might naturally separate them into 2 different types of problems. So one type of problem might be ones that your mind would categorize as aggressive. So these would be hits others, fights, talks back, and swears. And perhaps the other category would be a withdrawn category. Isolated, keeps to self, and timid would fit in here. The factor analysis works mathematically in almost the same way as our minds worked with that information. So what the factor analysis basically does is it searches for correlations between variables. It works in essence with a correlation matrix like we looked at in chapter 22. So it's trying to find groups of variables that are highly correlated with one another. And in essence, these will emerge as a factor. I suspect that, for instance, kids who tend to talk back are quite a bit more often to swear than are those who don't talk back. In other words, I suspect in our imaginary data set that talks back and swearing would be quite highly correlated. Indeed, I suspect all of these variables that we characterize as aggressive might be highly correlated, each with another. And the factor analysis is in essence searching for clusters of variables like that. And likely we'd find another cluster for our 3 variables that we thought indicated withdrawn behavior. So that if our data did indeed have 2 clusters of high correlations, one between the aggressive variables and another between the withdrawn variables, we would find, using the method of factor analysis, 2 factors, 2 sets of variables clustering together. And then usually the factor analyst, that's a fancy name for a researcher doing factor analysis, is a factor analyst would name those factors. We'd likely name them aggression and withdrawal. And now we've got basically 2 pieces of information. One is the aggressive factor, the second, the withdrawal factor. We've got two pieces of information that have captured almost all of the information that the 7 original variables conveyed. So we've reduced 7 pieces of information to 2 pieces. We've simplified things. And then the next step would be perhaps to see what different variables were correlated with our 2 factors. So for instance, we could look at boys and girls and look at do boys or girls score higher on withdrawn, or do boys or girls score higher on aggressive. So we could look at the relationship of gender to 2 dependent variables rather than, say, looking at the relationship of gender to 7 variables. So factor analysis reduces a larger number of variables to a smaller number, but when it does so, it loses minimal information. It simplifies and makes it easier for you to do subsequent analysis, though sometimes a factor analysis is an end in and of itself. That concludes Chapter 23. Chapter 24 is going to try to build a data interpretation model and try to integrate a good deal of the material in the text.